Okay, so welcome everyone. So today for this academic year's inaugural Karnov seminar, we're delighted to have Sri Raghu from Stanford. So Sri has been working on a number of very interesting and difficult topics, such as non-Fermi liquids, assorted criticality, dualities, and high temperature superconductivity. And today he'll tell us about a dual perspective on quantum Hall to insulator transitions. Sri, the floor is yours.
Okay. Can everyone hear me?
Yes.
Yeah, good. Thanks, Luca, for the introduction. It's a pleasure to be here virtually, although I would much prefer to be there in person. That's the world we live in. So as Luca said, my talk is about quantum Hall transitions. And, whoops. Okay. The work I'm going to present to you is based on some studies that I've done with some students who work with me. The first is Prashant Kumar, who just left Stanford and has joined a postdoc at Princeton. And then there's Pavel Nosov, who's finished his first year at Stanford. And then lastly, I'm going to touch on some work done by a bright undergrad named Kevin Huang. He did some of the numerical studies that I will mention. And he's actually applying to graduate schools this year. So those of you who are on admissions committees, I would urge you to take a look at his file. Okay, so the quantum Hall phase transitions involving the quantum Hall effect are among the oldest realizations of quantum critical phenomena. They've involved the integer quantum Hall states. They've involved fractional quantum Hall states. They've involved phase transitions from one quantum Hall state to another, and also from quantum Hall states to insulators. And the cartoon I want you to keep in mind is that you have a quantum Hall state in a 2D electron gas in a perpendicular magnetic field. We apply, as we change the magnetic field, the quantum Hall state can give way to either a different quantum Hall state across a quantum Hall phase transition, a quantum critical point, or it can give way to a quantum Hall to insulator. It can give way to an insulating state at the quantum Hall to insulating transition. Okay, so while these phenomena have been around for decades, our understanding of them still remains rather rudimentary. One example of this rudimentary understanding is if I, on average, polled the typical condensed matter theorist, most people would say the integer quantum Hall phase transitions involving the integer quantum Hall state must be free, because after all, the integer quantum Hall state can be described by free fermions. The insulator is certainly a free fermion state, and so why not the quantum critical point? We have descriptions of this based on spectral properties of non-interacting electrons in a disordered Landau level, and there's complementary perspectives based on percolation of droplets of quantum Hall state in an ocean of insulators and vice versa. And none of these have any interactions built into them. Okay. By contrast, any of you, no one in their right mind would say that there are free fermion realizations of fractional quantum Hall states. The fractional charge statistics, topological order, and so on, all those beautiful and profound features are features that cannot be obtained from free electrons. And so the naive guess that many condensed matter physicists would conjecture is that phase transitions involving the integer quantum Hall state and the fractional quantum Hall state should be completely distinct. They should be in distinct universality classes. Now that turns out to be a rather quick, too fast. And the fallacy underlying that reasoning is that it turns out that interactions are important even for the integer quantum Hall state. Okay, and phase transitions involving the integer quantum Hall state. So it's not obvious that this is a free theory, and this is certainly an interacting theory. So because this system also requires interactions, they can in principle be in the same universality class. Okay. More direct evidence that interactions are important at the critical point is the very basic observation that there's finite resistivity at the critical point. Okay. In 2 dimensions, the resistivity has the same units as resistance. So the resistivity is a universal amplitude associated with the phase transition. And what I'm showing you here is experimental data of the integer quantum Hall to insulator transitions. These are isotherms. And the point at which the isotherms cross is the quantum critical point. Okay. Now, Experiments are perhaps inconveniently done at finite temperature. So the very fact that you see a finite temperature resistivity tells you in this case that immediately that interactions are important. Why is that? It's because the founders of many body physics taught us how to compute what we mean by the DC resistivity or conductivity. You first take the thermodynamic limit, and then you take the zero frequency limit, and then you take the zero temperature limit, right? But in this problem, if for non-interacting electrons in a disordered Landau level, all states are Anderson localized, they don't contribute to conductivities, except at one energy where states are delocalized. Okay, so if you're sitting at the critical point, if the Fermi level lies on, say, this energy at which the states are delocalized, but since states at finite temperature within a width of the order of K Boltzmann times T of the Fermi level contribute to conductivities, the energy at which the states are extended contributes a set of measures zero to transport, and hence you would expect if you took the literal model of free fermions and computed the conductivity, you would find zero sigma XX at the critical point, which is clearly at odds with experiment where the resistivity is of the order of the quantum of resistance. Okay, so interactions are important for a finite resistance, a DC resistance. And even if they're irrelevant in the renormalization group sense at the critical point, they are sufficient to give you a finite resistance. A more direct evidence in favor of interactions being important are the observation of non-trivial dynamical scaling laws at the critical point. So these phase transitions, like all continuous phase transitions, involve a length scale that diverges. And in this context, this length scale is known as the localization length. And it diverges as a universal power law as you tune to criticality. The exponent is known as nu. In this field, nu takes on two meanings. One is this critical exponent, and the other is the filling fraction associated with the quantum Hall state. I'll make that distinction as we go on. Hopefully that will be clear. Associated with this length scale is a diverging time scale, which has an exponent in addition to nu, the dynamical scaling exponent. Okay, both of these exponents can be obtained from looking at the magnetic field and temperature dependence of the resistivity, which gives you the product of nu times z, as well as the nonlinear IV characteristics, which can give you nu independently from z. Okay, and these experiments have been done for integer quantum Hall states and as well as fractional quantum Hall states. And both of them seem to be roughly comparable to each other. The exponent nu, for instance, is close to 2.3. And the dynamical exponent in these class of experiments seems to be z equals 1. Okay? And there are other experiments as well by looking at the width of the transition region as a function of temperature. All of these seem to corroborate z equals 1. Now, if you took the non-interacting model seriously and computed these exponents, you would find, for instance, z would not be 1. That cannot come from the free fermion problem. In fact, the free fermion problem, everything is specified once you know the density of states. And the very basic fact that the density of states at the critical point is finite tells you that since the density of states is the number per unit volume per unit energy, if that's finite, it tells you how energies behave as a function of length, and always depends as length to the d. And hence, z would be d, which is in this case 2. And so what people said in the early days of these experiments is that to get z equals 1, what you need is 1 over r interactions. So this is a natural energy scale that goes like 1 over length. And if that length is the localization length, that would provide z equals 1. What I'm going to do today is provide to you a slightly more sophisticated version of this argument. Okay, but for now, what I want you to take away is that interactions are important even for the integer quantum Hall transition. So there was this old review by Shivaji Sondhi and Steve Gervin and others. At the end of that review, this is from 1997, I just want to quote some excerpts from it, where they talk about what are the open problems. And so here are 3 quotes. The first is, it says that z equals 1 strongly suggests that Coulomb interactions are playing an important role. The second comment is that the a priori validity of superuniversality, which is to say that the integer quantum Hall states and the fractional quantum Hall states, transitions involving them are in the same universality class. So the a priori validity of this is still unclear. And so in summary, theorists, they say, have their work cut out for them. Okay, and not much has changed since then. So the main point of my talk is that, the theory of quantum Hall transitions is very much in a primitive stage. Most studies neglect interactions. Interactions are important for finite electrical resistance at the critical point, the correct dynamical scaling laws, and also if you want to compare fractional versus integer transitions, okay? A theme of my talk is that the composite fermion representation will readily address these three issues. We haven't solved the problem. There's still much to be done. For instance, what we don't know yet is how interactions will affect the localization length exponent nu, but nonetheless, we can make statements of all three of these issues, okay? Which are much more difficult to address when you work in electron coordinates. Okay.
Sri, can I ask a quick question?
Yes.
This is Rudro. Sri, in one of the previous slides, you mentioned this, this thing that the dynamical critical coefficient has to be 2, exponent has to be 2 based on non-interacting electron theories.
Right.
But in the presence of a magnetic field, can we make that statement?
Yeah, you can, because at the critical point, that if the density of states of the Landau level is finite, which it is in non-interacting descriptions of disordered Landau levels, that's sufficient to have z equals 2.
But that's not really a theory where the density of states is given by electrons with momentum k. It's for example, if there is no disorder, it would be a delta function.
Right. So the delta function is broadened, right, into some finite density of states.
What I'm trying to say is that I'm just asking why the exponent needs to be 2. Well,
the density of states doesn't require translational invariance. It's just some, you put your spectrum you put particles in a box. They don't have to have momentum conservation. And you ask how many, you just bin the energies, and you can do that in any case, even in this present case, right?
Okay, makes sense.
Right.
Thank you.
Any other questions? Okay, good. Thanks for the question. So here's the problem we want to solve in the language of the knobs that the experimentalists use, okay? So we have a 2D electron gas in a strong perpendicular magnetic field with disorder, say a random potential that couples to the density of electrons, and interactions, say 1/r interactions. Now, this problem has no small parameter. If we want to study it numerically, we'll be fraught with finite size effects, and when we're studying critical phenomena, we really want to be at long distances, so that's a formidable challenge. Instead, let's think of this problem in a different representation, known as the composite fermion representation, okay? So there are two choices of employing this composite fermion representation for this problem. The first is to view composite fermions as obtained from electrons and imparting a singular gauge transformation known as flux attachment. And this was pioneered by Halperin, Lee, and Reed back in the 90s. And there's a more recent theory by Sohn, the Dirac composite fermion theory, which presumably many of you are intimately familiar, which views the composite fermions as dual vortex degrees of freedom, okay? Now, both approaches can be used. They both motivate a much more systematic approach to this problem, a traditional mean field plus fluctuations approach that we teach in our statistical mechanics classes for phase transitions. And it turns out that within mean field theory, both composite fermion theories give identical predictions, okay? But they differ when you include fluctuations in an interesting way and go beyond mean field theory. And I'll touch on that as I go along. Okay, so I'm gonna predominantly use the Dirac composite fermion theory. So just to quickly recap what that theory is about in terms of the view that we want to take in this talk, the idea is that, if you look at non-relativistic electrons in the lowest Landau level, their wave functions are very similar to Dirac electrons in their lowest Landau level. Okay, so of course Dirac electrons have spinners, non-relativistic electrons don't, but in the lowest Landau level, only one component of the spinor has any non-zero support. And so for all practical purposes, the wave functions behave as just some scalar, some Hermite polynomials. And so we can ask what happens if we think of the quantum Hall problem in the lowest Landau level in Dirac electron representation. This has an additional advantage that it can explicitly preserve the symmetry of particles and holes with respect to a half-filled Landau level. Okay, so the idea is to think of this Dirac electron in a background external magnetic field. This 1 over 8 pi ADA is a consequence of the parity anomaly in 2 + 1 dimensions. If you wish, if you put this on a lattice, there would be a massive partner that would generate this object. Now, in recent years, we know that this theory is dual to a gauged Dirac electron, a Dirac composite fermion rather, where this object is coupled now to a dynamical UN gauge field, little a, and then there's these additional terms which are required for getting the right electromagnetic response. So if you look at, if you differentiate this Lagrangian with respect to background fields, you'll get the density of electrons, the Dirac electrons, and they're related to the dynamical flux, little b. And furthermore, if you look at the equation of motion of the time component of little a, that will tell you how to relate the Dirac composite fermion density in terms of the external magnetic field. We will need this because what I'm about to do next is take these theories and add disorder and interactions to them. Okay, so we're going to add disorder by shifting the background field, the time component, by some quenched random potential V of R. Okay, and when we do that, the Lagrangian for the Dirac electrons will shift and obtain a random potential coupled to its density. Okay, we can do the same thing in the dual composite fermion representation. And since the density of electrons is related to the flux of composite fermions of the little a, curl of little a, the disorder potential is V of R times B of R. Okay. But now, how does this couple to the fermions, the composite fermions? So what we have to do is, since the flux little b is a dynamical variable, and whereas V of R is a quenched random variable, it sort of sources a quenched random component of the flux. So in order to implement that in the theory correctly, what we're going to do is take the dynamical U1 gauge field, view it as a piece that's fluctuating and a piece that comes from quenched randomness, A prime, such that the curl of A prime would be this random B of R that's sourced by V of R. Okay? So in terms of the fermions, what the Dirac composite fermions are seeing as far as disorder goes is a random vector potential in addition to a fluctuating vector potential. And this random vector potential will be chosen out of some, say, Gaussian white noise distribution where NF is the density of states at the Fermi level and tau is related to the mean free time between scattering events of the disorder. Okay, so then we ask about interactions. So the interactions in the electron coordinates are density-density interactions. Since the density of electrons is related to the flux, this will be some flux-flux interactions in the Dirac composite fermion representation. Okay, so since this is quadratic in the gauge field, the interactions manifest themselves as gauge fluctuations. As you can see that this is going to be some gauge boson kinetic term. So to put it all together, oh, sorry, I should say, in the Coulomb gauge, where this dynamical gauge field has a temporal piece and a transverse piece, the interactions have a purely transverse representation. So for instance, for the case of 1 over R, so E star includes the dielectric constant and so on. The interaction can be written purely as a transverse gauge boson kinetic term with mod Q. For contact interactions, there'll be a Q squared term in this action. Okay, so to put it all together, what we want to study is a gauged set of Dirac fermions coupled to some dynamical and background fields with disorder and interactions. Now, the first question you may ask is, why would anyone do this? Because this is a strongly coupled theory. Isn't that going to make the problem much harder? What I hope to show you is that it's actually the other way around. Things can be easier in this representation, say, than the electron representation. And you'll see why. So the first thing I'm going to do is talk about the mean field approximation within this. Are there any questions so far?
Just a naive question, Sri.
Yeah.
So without disorder, the interactions would probably be irrelevant. But here is the point that there's going to be some interplay.
You mean the 1 over R interactions?
Yeah, density.
Well, you know, if you're in, they're actually marginal in the clean limit, right? This interaction here, sorry, this one, and this is going to be relevant. So this leads in the clean limit would lead to some non-Fermi liquid fixed point with, say, omega to the 2/3 self energy and all of that. This would lead to a logarithmic correction, the marginal Fermi liquid. But disorder indeed does change things. It, on the one hand, mitigates the effects of interactions, but also it makes the problem run away to strong coupling, as I'll talk about. So it is, the disordered and the clean problems are different.
Okay.
All right, so in the mean field approximation, what we do is we treat the gauge dynamics only via their equations of motion. So this is the theory in full again. And since I'm a condensed matter physicist, I always like to imagine myself putting things on a lattice so that I really understand things. I could tell a computer what to do in principle. So what I'm going to do is reordered some terms in this Lagrangian to make sure I have a proper UV regularized theory that I can analyze in mean field theory. So to that, what I'm going to do is add and subtract a -1/2 ADA. And by the way, in this talk, I'm only interested in local properties. So the improperly quantized Chern-Simons levels can easily be corrected by adding additional fields, but I'm not going to bother with that since I'm not interested in global properties so much. Okay, so I'm going to add and subtract a little a d little a term. And so that these terms here get shifted, and the new Lagrangian involves what I call L psi, which is this Dirac fermion plus the level half. There's L gauge, which is this term here, and then the same as before, disorder and interactions. Okay, so this can be thought of as now a lattice model for a Dirac fermion coupled to a fluctuating vector potential, with this being the massive partner. Now, associated with this Lagrangian will be a mean field Hamiltonian, which consists of 2 flavors. There'll be a light flavor that generates this term here, and a heavy flavor with some mass m, which generates this term. And the mass m will be far greater than the chemical potential that both flavors are subjected to. Okay. So in the mean field theory, to get the phase diagram, what we will do is we're going to ignore gauge fluctuations, and the tuning parameter for the transition will be some average magnetic field. Okay, so there was a quenched random field, B of R, and I'm going to now allow for it to have a uniform piece, B0. Okay, and I'm going to tune, the critical point will be at B0 = 0. So here's how we understand the phase diagram. If we put the Fermi level somewhere, because of disorder, all finite energy states are localized. They don't contribute to any transport. But since there's a uniform magnetic field, this problem has some number of 0 modes by an index theorem. The number of 0 modes is given by the number of flux quanta of B0. And this 0 mode band acts like a Landau level. So it generates some Hall conductance. And since it's at 0 energy, it'll be half filled. So depending on whether we apply positive B0 or negative B0, the Hall conductivity will be ± a half in units of E²/h, or 1/2 pi. So if we look at the contribution from just the light fermion, sigma xy, the Hall conductance is just 1/4 pi times, is ± 1/4 pi. Okay? 1/2 pi here is E²/h. But then when we include the massive partner, the UV regulator partner, that always generates a -1/2 in units of 1/2 pi. So this phase boundary for positive magnetic field, the Hall conductance is 0. So that's the insulator of composite fermions. For negative magnetic fields, the Hall conductivity is -1/2 pi. That's an integer quantum Hall state of composite fermions. And at the critical point, the light mode doesn't contribute to the Hall conductance. It has a sort of time reversal symmetry. And all the Hall conductance is obtained from the massive partner, which is -1/2. Now the fact that, so we see that the integer quantum Hall to insulator transition is captured in the composite fermion representation as a dual integer quantum Hall to insulator transition. Now, the fact that at the critical point, the Hall conductance is -1/2 in units of E squared over H is significant. And it's because if we think of the Laughlin gauge argument, Laughlin taught us that if all states are localized at the chemical potential, the Hall conductance must be an integer multiple of E squared over H, or 1/2 pi. So the fact is that since we have a half integer Hall conductance, by a corollary of this theorem, implies that states must be delocalized. Now, for this argument to hold, I could have put the chemical potential anywhere in this at finite energy, provided that it was less than the mass of the heavy fermion, the partner fermion. So what this tells us is that for any chemical potential from 0 to the mass scale of the massive partner, all states must be delocalized at the critical point. Okay, and in my view, this is a complete game changer when we think of quantum Hall transitions, because while in electron coordinates, there's only one energy at which states are delocalized. In the composite fermion theory, all states are delocalized, and there's absolutely no subtlety for there being a finite DC resistance, because there's no subtlety. All states are delocalized, they all will contribute to transport. Now, because the composite fermions have a finite resistivity, there's a relationship between the composite fermion and electrical resistance, which is given here. This is the composite fermion resistivity tensor. This is the electrical resistivity tensor at criticality. And this epsilon is the unit antisymmetric tensor. So it's a pure Hall response. So this tells us that since the composite fermion resistivity is finite, the electrical resistivity will also be finite. Okay? So that's how we get a finite DC resistance in the mean field approximation for electrons. I again want to remind you that this is by no means obvious in electron coordinates. So since we have now a well-regulated theory, we can put it on a computer. This was done in recent work that we're about to post with Kevin Huang and Prashant Kumar. And what we found is that when we study this Hamiltonian, as we tune B naught, the localization length exponent nu is 2.56, which is very close to the accepted value. It's in the state-of-the-art computations of non-interacting electron quantum Hall transitions, known as the Chalker-Coddington model. And we also looked at what are known as multifractal wave function behavior, where we look at the states at the critical point at the Fermi level, and we look at what are known as participation ratios. These are just the wave functions to some exponent, and they have some well-defined form, which is also in good agreement with the Chalker-Coddington model. So what this does for us is that it emboldens us that the dual theory that we're studying has all the right physics built into it at the mean field level. But now we can go further and talk about fluctuation effects. Okay, but before I do that, let me tell you one beautiful advantage of thinking about composite fermion representations is it enables us to compare the integer and fractional quantum Hall transitions readily. So what I'm going to do next is think of the mean field approximations to a class of fractional quantum Hall states known as the Laughlin fractions, where the filling fraction, this is not the localization length exponent, this is the filling fraction, the ratio of the density to the flux density. The filling fraction 1/2m minus 1. So for m equals 1, we capture the integer, but for higher integers, we capture 1/3, 1/5, and so on. So we want to consider their transitions to the insulating state. And to do that in the composite fermion representation, all we need to do is change L gauge. Okay, the only thing that changes is the factor of m in the denominator. Okay, there was a recent effective field theory proposed by Hart Goldman and Eduardo Fradkin, which generalizes Sohn's Dirac composite fermion theory to look at higher order fractional quantum Hall states at quarter filling, 1/8 filling, and so on. Sorry, transitions at 1/4, 1/8 filling. And so in this representation, the matter part of the Lagrangian is doing exactly the same thing as before. It's only undergoing an integer quantum Hall to insulator transition. These other objects are important for gauge fluctuations. They're also important for the critical resistances because, as before, there was a dictionary between composite fermion resistivities and electrical resistivities. M enters in that dictionary to relate the two resistivity tensors, but the mean field exponents are determined only by the matter fields undergoing an integer quantum Hall to insulator transitions. So we would expect the same exponents for integer and fractional quantum Hall transitions. Okay, and this is a sort of a trivial form of super universality. You should think of the analogy to the Landau theory of phase transitions, where all phase transitions that are continuous have the same exponents, regardless of whether we're breaking discrete or continuous symmetry because of the fact that we're ignoring fluctuations. It's exactly the same here. So the mean field theory that I've discussed so far tells you that the composite fermions have finite conductivity at the critical point. The transitions, when we view in this approach, are trivially superuniversal. The conductivities depend on which fraction is undergoing a transition, but the dynamical scaling laws are always governed by the density of states. So Z would be 2, and nu would be 2.6 for all transitions. So next, I'm going to include fluctuations. Are there any questions so far? Okay, so now we're going to talk about what role fluctuations.
Question? Sorry.
Did I hear some?
Yeah, Subir speaking here. Can I ask a question?
Yeah, please.
Can you at least just show the Hamiltonian for which you did the numerics?
Yeah.
Just the mean field theory, so I understand it.
Yeah. So it's.
No, I don't need a justification. Just what is the Hamiltonian?
The Hamiltonian is just a Dirac fermion at finite chemical potential in a random vector potential.
So A prime is a random vector potential with net zero flux, or what?
Yeah. Sorry. There can be a uniform flux. That's the tuning parameter. At the critical point, the net flux vanishes.
Okay, so then B naught is the net flux of A prime.
Yeah.
And you claim that in this theory, this is a free fermion theory.
Correct.
And at some point, you said all states were extended?
At the critical point.
Okay, so when the net flux is 0,
correct,
then all states are extended in this theory.
Correct.
Okay. So these are, these are very unfamiliar claims to me. These are well established, or they come from numerics, or this is one of your discoveries, or?
This comes from numerics. So there were some old studies by Shankar, Fisher, and Ludwig, where they had a Dirac fermion in a random vector potential.
Yeah, I remember that paper. Yeah.
That was at 0 chemical potential. Mm-hmm. And what you get is a line of fixed points with varying disorder. But the line of fixed points are gone the minute we deform the theory with a uniform chemical potential.
Chemical potential meaning B naught here.
No, that's a magnetic field. There's a chemical potential and a uniform magnetic field coming from the curl of A prime. Mm-hmm. So there's a Dirac cone which has some finite energy, finite Fermi energy.
Okay, and the moment B naught becomes non-zero, you get all states become localized.
Localized, correct.
Okay, thank you.
Okay, good. Thank you. All right. So now let's look at fluctuation effects. So before disorder averaging, we had this Lagrangian. We had matter, the gauge fields, and disorder and interactions. So what I want to do now is disorder average, look at disorder average quantities by averaging the free energy, the log of the partition function, with respect to the disorder probability distribution. And that's done by this replica trick over here, where we take n copies and take the limit as n goes to 0. So when we do this, we take this theory, the Dirac fermion with gauge fields, disorder, and interactions. We replicate and integrate out the disorder. There's an exact operator identity relating this Lagrangian to this action here. So S gauge is the action associated with L gauge. The interactions are the actions associated with L int. And then there are these fields Q, which are perhaps unfamiliar to some of you. But what they are Hubbard-Stratanovich fields that are obtained from after disorder averaging. Okay. Now this problem has a gauge coupling. So this is where the fields Q couple, since the original gauge fields couple to the fermion. When we integrate out the fermion, we get this fermion trace log. And so this theory involves gauge fields coupled to these Q matrices. So the Q matrices are matrices that have row and column indices corresponding to replica number indices, A and B. So you can rotate in replica space. And then they have two time labels, T and T prime, that come after we disorder average, we integrate over a distribution that only depends on space. Now, we can Wick rotate this theory into Euclidean space and put the system in a finite box of length 1 over temperature. Then the frequencies would be discrete. These are the so-called Matsubara frequencies, and they act as row and column indices for this matrix Q. So this is some complicated matrix, has replica and Matsubara indices, but it lives in space, 2 plus 0 dimensional space. And the effective field theory for Q is going to be some nonlinear sigma model. Okay, so this is the full theory. This is just an exact rewriting of the disordered average quantities in the replica approximation. So it's maybe not exact, but it's a rewriting once you disorder average. And now what I want to do is think of this within some double asymptotic expansion. The first will be a saddle point expansion of Q with G equals 0. And the second will be an expansion in powers of G, the coupling between Q and the transverse gauge field. So when we look at the saddle point expansion, there are standard methods. What you find is that the matrices Q have a saddle in which Q squared is 1, their trace vanishes, and their Goldstone manifold is this Grassmannian, where the n here corresponds to a replica n. Okay, and the effective action for Q is decoupled from the effective action for the gauge bosons that are S gauge and S int. The effective action for Q has this nonlinear sigma model form. So there's a linear derivative for Q and quadratic spatial derivatives. And then there's a topological term, which is related to the Hall conductance. Okay, and this term here is related to the longitudinal conductivities. And the conductivities act like stiffnesses for the sigma models. Now, when we do the second thing, when we expand about powers in G, what we're going to do is gauge this nonlinear sigma model for Q, effectively replacing all derivatives by covariant derivatives. And the corrections we would get involve sigma xx times this first term, and then there's a second term. But sorry, there's an important...
Can you tell us what was G originally? I lost track of.
G is this quantity here, which is like a gauge charge between the fermions, the fermion currents, and the gauge field. Does that answer your question?
It's the charge of the fermions? What was it originally before integrating?
So what G will be is either 0 or 1, okay? When G is 0, but G is 0, the gauge field were decoupled from the fermions, okay? So remember, there was a covariant derivative, the slash.
Yes.
And so G is 1 effectively because it couples to psi bar gamma mu psi times A prime.
So what does it mean to do a series expansion in G if it's 1?
Well, we're doing asymptotic expansions, you know. I have no justification for that. It's basically, we are looking at powers in the coupling between the matter fields and the gauge fields. Okay, it's a perturbative expansion. Okay, so what you'll find though, to any order in G, is that there is no corrections to the theta term, the topological term for Q. Notice that the corrections at low orders in G only correct sigma xx, but they don't correct sigma xy. And we know this as an exact statement, even at G equals 1. And the reason is this. There's a symmetry in the problem. The topological term is related to sigma xy. Its coefficient here is sigma xy here. And when we gauge this term, these derivatives would get promoted to covariant derivatives, and that would mean that gauge fluctuations would renormalize sigma xy. But in the Dirac composite fermion theory, the massive degrees of freedom are the ones that are responsible for sigma xy. There's a light Dirac fermion which has time reversal symmetry, so it doesn't have any Hall conductance contributions. All Hall conductivity comes from the heavy massive partner, which is at some high energy scale that doesn't couple to the gauge bosons, it doesn't couple to the disorder, and it by itself preserves a half integer multiple of sigma xy that is unaffected by gauge fluctuations. Okay, so gauge fluctuations do not change the DC Hall conductivity in the Dirac composite fermion theory. By contrast, if we repeated this exercise with the HLR theory that I alluded to in my talk, in this theory, Hall conductance is entirely from the light modes at the Fermi surface. And so here you would have a gauged topological term. Okay, so this is the distinction between the Dirac composite fermion theory and the HLR theory, okay, in the form of their topological terms in the presence of gauge fluctuations. What this means is that in the HLR theory, the Hall conductivity is a running coupling at criticality, whereas in the Dirac composite fermion theory, at criticality, sigma xy is -1/2 and it doesn't run. So since sigma xy is -1/2, what this implies, again, from Laughlin's gauge argument, is that the Dirac composite fermions remain delocalized even with gauge fluctuations, okay? And what that implies is that there's a finite conductivity of composite fermions, and that gives a source of dissipation to the quantum critical point. There's furthermore a finite density of delocalized states. The density of states of these modes are finite, and that'll give rise to Debye screening. Okay, and those are the two physical objects that I want to actually look at now. Okay, are there any questions? All right. So I want to look at first the implication of Debye screening. There's a finite compressibility coming from a finite density of states of delocalized composite fermions at criticality. And what that means is that, what this will mean for us is that the fluctuational corrections from Chern-Simons terms will be irrelevant. The reason for that is we have our L gauge and L int here. So after we look at quantum corrections, the fact that there's a finite density of states enters as a sort of mass term for the temporal component of the dynamical gauge field. Okay, that's the compressibility. In addition, there are Chern-Simons terms coming from L gauge, which are cross terms in the temporal component and the transverse component. Q is momentum. And there are interaction terms like 1/r interactions, which are purely in the transverse channel. Since the temporal piece is gapped out effectively by the compressibility, you can integrate it out and you see that all corrections from the Chern-Simons, fluctuational contributions from the Chern-Simons terms are irrelevant. They enter as subleading corrections to the gauge boson action. And so while we can't tell you what the critical exponents are, we can say that with the presence of 1/r interactions, the Chern-Simons level enters only as a subleading correction to the effective action for the transverse gauge boson. Okay, and what that will tell us is that, Subir?
So the critical theory was Dirac fermions coupled to flux disorder.
Correct.
Is that, and this is just static flux disorder where you can ignore the dynamic fluctuations of the gauge field.
At mean field, but at fluctuations, we'll have to include dynamical corrections.
But isn't chi naught 0? What is the density of state of the Fermi energy? 0, right?
No, this is at finite chemical potential. Right? So there's some density of states and they are delocalized. And so that's some number, order 1 number.
Okay, so you're back to the problem of just ordinary fermions with the finite density of states.
Yes.
The presence of flux disorder.
Yes.
Which is the original integer quantum Hall transition, is it?
Yeah. Yeah, if you neglect all the Chern-Simons terms and so on in the Lagrangian, it is just an integer transition of composite fermions.
Okay.
Any other? Did I answer your question, Subir? I'm not sure I.
It's mostly my own confusion. I'm just going to have to think a bit more. Thanks.
Okay. Okay.
Sorry.
Maybe we can chat later.
A silly question. What's going on with this chi naught a naught squared interaction? It doesn't look gauge invariant.
Okay. So there's an entirely equivalent way of rephrasing everything, which is the following. Okay. We have a finite density of composite fermions. The transverse degrees of freedom, this term here in L int is just a current interaction. It's decoupling a current interaction of composite fermions. The Chern-Simons term can be viewed as decoupling a current density interaction. And lastly, this chi-naught term is just a density-density interaction. This is like in ordinary metals, the electric field gets screened out by the finite density of states of the metal. So this is saying that density-density interactions between two test charges get screened. That's all it's saying.
But why are you allowed to write down gauge non-invariant terms? A is a gauge field, right?
Yeah.
So isn't this term illegal?
It's not illegal for non-relativistic systems which have finite density of states. Maybe there's a better way of saying it, but a priori, this is a manifestly gauge invariant way of describing the problem.
Is this the action in some gauge? Or the Lagrangian in sub gauge?
Yeah, so
otherwise it's just manifestly not gauge invariant.
Okay, I think there is a way of saying this, which is that because there's a finite density of states, when you look at the quantum correction, which is the bubble, which has external legs corresponding to only the time component of the gauge fields, this is like the pi mu nu, it involves only the field strengths, okay? It's gauge invariant. It's like the electric field squared, but it's non-local because of what would have been the Fermi surface and the clean limit, right? And so that non-local term looks like 1 over q to some power. I guess it must be q squared. And so that's why it looks like it's not gauge invariant, but it can be written as a non-local term involving an electric field. Does that help with this issue?
I don't really understand it, but I don't want to hold you up.
We can discuss it more. I think what I said is correct. It can be stated in a gauge invariant fashion. Okay. The other thing I want to talk about is dynamical scaling laws. How am I doing with time, by the way? I must be nearly finished.
You still have about 15 minutes.
Oh, 15 minutes.
Yes.
I see. Okay. So I want to get back to this issue of dynamical scaling. Okay. So the minute we have 1 over r interactions, the gauge boson has this non-trivial, this new kinetic term, right? It's not governed by Maxwell term anymore. So this is Q linear. But now if we look at quantum corrections to it, and since this is the transverse gauge boson, the quantum corrections will come from the current-current correlator. Now, since I told you that states were delocalized at criticality, by Kubo's formula, the current-current correlator is just the frequency times the longitudinal conductivity, sigma xx. Okay, I can't tell you within this model, since I'm looking at saddle point expansions of the theory, I'm looking at in a perturbative regime. I can't tell you what sigma xx is, but I can say that it's not 0 and it's not infinity. So it's finite, and that's sufficient for me to argue that omega will scale like Q. Okay, now this is not Lorentz invariant. The gauge boson is overdamped, but it enjoys z equals 1 scaling. Okay, we can repeat this argument for short range interactions. The only thing that changes is Q squared. Q becomes Q squared in the transverse gauge propagator. And so now we can see that again, the conductivity will be finite by Kubo's formula, and that would set omega goes like Q squared. The boson is again overdamped, and Z would be 2. Okay, so now we want to, if we want to construct an ultimate scaling theory of these quantum Hall transitions, they involve 3 running couplings. Okay, one will be sigma xx, the other sigma xy, and the third will be E squared, the strength of the interactions. Now, if we work within the Dirac composite fermion theory and tune to the critical point, sigma xy, I've already argued, doesn't run from gauge fluctuations. It's just pinned at -1/2 of the composite fermions in units of E squared over H. So there's 2 running couplings, sigma xx and E. Okay. Now, we don't have, the nonlinear sigma model has a theta term that leads to some flows away from weak coupling towards strong coupling. And so sigma xx, I can't tell you what it is, but I can tell you that it's finite. So even though we don't know the answer yet, we know the dynamical scaling laws are present. And we also know that because of Debye screening, the transitions of fractional states and integer states will be in the same universality class. Okay.
What does the word super universal mean?
Super universal means that phase transitions of the Laughlin fractions, 1 over 2m minus 1 filling fractions, phase transitions involving them and between them and the insulating state are in the same universality class as those involving the integer quantum Hall state. Okay. Now the critical resistances are different, but the critical if the transitions were super universal, all critical exponents, say the localization length divergence, the dynamical scaling laws would be the same at the critical point. Okay.
Okay.
All right. So we haven't been able to extract how interactions will change the localization length exponent due to gauge fluctuations. Since the conductivity enters via the Kubo formula into the gauge boson propagator as a quantum correction, the gauge boson spectral function, the finite size scaling behavior of the gauge boson spectral function should in principle be able to tell us what nu would be, but we haven't managed to succeed in extracting that yet. So now let me summarize the talk in this pictorial fashion. Okay. This is the cartoon of what the renormalization group flows should behave like in the vicinity of the quantum Hall to insulator transition at 0 temperature with 1 over R interactions at the critical point. Okay. Within the Dirac composite fermion theory, there are 2 running couplings. One is related to disorder, inverse sigma XX, and the other related to interactions, inverse charge. Okay. Electron-electron interactions. Along this axis here, there are no gauge fluctuations, and the exponents are governed by the non-interacting, or equivalent to the non-interacting quantum Hall transition, known as the Chalker-Coddington model. The dynamical scaling laws are governed by the density of states, so Z would be 2. But here, the interaction effects must be relevant and give rise to this new interacting disordered critical point, which has Z equals 1 scaling. And we can also tell you that with 1 over R interactions, integer quantum Hall states and Abelian fractional quantum Hall states must be in the same universality class, but we have not yet managed to obtain the divergence of the localization length exponent. Okay, I can stop here. Thank you for your attention.
Okay, thanks, Sri. We have time for a few questions.
Nice talk, Sri. This is Rudro.
Hi.
Just wanted to understand this point, which you made at the very beginning of your talk, which is that in order to understand the exponents for the plateau transitions in integer quantum Hall states, I think you said that we need to take into account interactions. Is that true?
Yes. If you want to compare to experiments, that is absolutely correct.
I see. I see. And one of the significant points you're making is that the dynamical critical exponent is different from what you would calculate in a model of Landau levels with disorder.
Correct.
As compared with experiments.
Correct.
I see. Thank you.
Sure.
Okay, I can ask a question. So if I understand correctly, what eventually led to the Z equals 1 was first that you had some kind of non-renormalization argument for sigma xy, proving that it wasn't, that it was not an integer.
Yeah.
And then some converse of Laughlin's argument tells you that sigma xx, that things will be delocalized and sigma xx is finite. And then finally it's this action that fixes Z to 1.
Yeah.
But maybe this is just a naive question, but things are strongly interacting. So why should we balance both of these terms? Should we be maybe looking at it, I don't know, quartic term or some other thing? And
very good. Okay, so I can tell you one thing. When you feed this object back into a fermion self-energy. This is not really going to address your question. You feed it back to the fermion self-energy. What you get is a Fermi liquid correction. Okay, the self-energy is no longer singular with the Z=1 gauge boson fed back to the fermions. So that at least tells you that things are self-consistent. But let me also say that your argument, yes. So if we are tacitly assuming that the kinetic term of the gauge boson sets the dynamical scaling, not some interaction. It's not some incoherent piece with some anomalous dimensions and so on. So that is I accept that comment of yours actually. Yeah, that's a valid comment. Let me just say this though: if we didn't have disorder, the Kubo formula would be replaced by Landau damping. This gauge boson would have Z=3 scaling then, because Landau damping goes like omega over Q, and it would have Z=2 scaling because of the Coulomb interaction. And that is a perfectly well, that leads to a perturbatively accessible description in terms of a fixed, perturbatively accessible fixed point. Now, with disorders, things run strong due to the theta term in the nonlinear sigma model. So it is a fair point that you make that it's not obvious that the gauge boson remains, like dominated by its Gaussian piece. So I don't have an answer to that question, actually. A good answer to that question. It's a good comment.
Okay, thanks. Any other questions for Sri? Okay, if not, let's thank Sri.
Thank you for your attention and all the good questions.
Yes, and maybe we can take a 5-10 minute break to have a drink and come back for more discussion.
Sounds good.
I'll stay online so that this thing doesn't collapse into
Okay.
a black hole. Okay.
I'll just go get a cup of coffee.
Yeah, sounds good.